Hi, my name is Samuel, and I was this year's director for the Fixed Challenge team in PolyCortex. The Fixed Challenge involves the creation of an acquisition board for biosignals. I will present to you the electrical architecture of this year's pipeline, the software, and the challenges we faced due to the coronavirus pandemic. PolyCortex has a short but consistent history of creating high-quality acquisition pipelines for EEG. These pipelines are composed of two main components, an acquisition printed circuit board and a companion software. The printed circuit board amplifies and cleans up the signal analogically, then digitizes it. The digitized signal is sent through serial communication to a computer running the second component of the pipeline, the software, which receives, displays, and records the signals. The software is also capable of running multiple post-processing treatments, including digital filtering and frequency analysis. However, plug-and-play ability was always lacking from the previous versions of the PolyCortex acquisition pipeline. As a matter of fact, the printed circuit board was dependent on multiple pieces of equipment to properly function, including a dual-rail power supply to provide the positive and the negative voltage levels needed to power the operational amplifiers in the circuit, the microcontroller development board to bridge the digitization ADC to the computer running the display and recording software. In order to be able to more conveniently use the acquisition pipeline in PolyCortex's future projects, the Fixed Challenge team for 2020 decided to focus its efforts on research and on developing an acquisition board which can communicate and be powered through a USB port. This necessitated the incorporation of a power supply circuit and a microcontroller on the board, in addition to the usual amplification and filtering circuitry. EEG signals are extremely small, only in the tens of microvolts range, and are particularly susceptible to being coupled with noise. This noise mostly comes from two different sources: common mode noise and electromagnetic interference, and is often of a bigger amplitude than the signal itself. As such, the signal coming from the electrodes needs to be filtered and amplified in a way that keeps the differential signal while removing as much of the common mode noise as possible. To do so, it gets fed directly into an instrumentation amplifier stage when it reaches the board. The instrumentation amplifier design chosen for this year's submission is based on multiple operational amplifier circuits. The design is a multi-channel extension of the classical 3 op-amp instrumentation amplifier design, configured with a gain of 1000. Precision resistors were used in order to ensure its proper function. The instrumentation amplifier was implemented using the OPA2202 integrated circuit from Texas Instruments, which contains two op-amp circuits. This means one IC is required per EEG channel, plus one more IC for the reference circuit. The design, while performing extremely well in SPICE simulation, proved to be a disappointment when tested on the circuit board. In the future, off-the-shelf instrumentation amplifier chips will be preferred for the initial amplification stage. After the initial amplification stage, we need to remove any DC component from the signal in order to preserve only the differential information. To do so, we employed a simple first-order passive low-pass filter with a cutoff frequency of 0.5 Hz. A notch filter is essential in our design since we are not using a driven right-leg circuit, which would reduce the parallel common mode noise. In the absence of a right-leg electrode, the instrumentation amplifier will still filter most of the common mode noise, but the signal needs to be further filtered to remove the highest source of common mode noise, the power-line 60 Hz signal. Unfortunately, this frequency is around the middle of biosignal's frequency. This means we can't use simple high-pass or low-pass filter to remove it from the signal. Instead, we have to use a notch filter. Fortunately, however, the signal is quite precisely tuned at 60 Hz, so we can use a notch filter with a high quality factor to filter it, in order to preserve the surrounding signal as much as possible. The filter design we chose to use is an active notch filter based on the twin T topology, but with an adjustable quality factor. It uses two op-amp circuits to induce feedback in the middle branch of the twin T, which enables this adjustability. A similar notch filter design was used in the previous version of PolyCortex's acquisition boards, but with the high quality factor required, we had trouble configuring the notch filter at a center frequency of 60 Hz, even when using high precision components. This led to inefficacy of the notch filter and to leakage of 60 Hz noise in the signal. We corrected the problem by adding a trim potentiometer to the middle branch of the filter, which allows for precise tuning of its center frequency. This adds an initial calibration step when first using the board, but ultimately enables complete removal of the 60 Hz noise. This filter was implemented using the OPA2202 integrated circuit from Texas Instruments, which contains two op-amp circuits, which means only one of these ICs is used per EEG channel for the notch filter stage. Since EEG signal is limited to the few tens of hertz frequency bands, we don't need to preserve frequencies higher than 100 hertz in the signal. Furthermore, it is important to remove high frequency noise from the signal if we want to digitize it in order to avoid aliasing effects in the digital signals. To do the anti-aliasing filter step, we implemented a second-order active inverting Butterworth filter in the silent key topology with a cutoff frequency of 100 Hz. This filter is repeated twice in order to get a fourth-order non-inverting filter. The OPA 2202 from Texas Instruments is also used for this filtering step, and we use one chip per biosignal channel. After being amplified and filtered, one of the last steps needs to be done analogically before digitizing the signal. Indeed, at this point, the signal is completely devoid of any DC components and is centered around 0 volts. The digitizing circuits require the signal to be completely saturated above 0 volts, and so we need to add DC components to it. This is done with an op-amp adder circuit and a voltage reference. Since the peak-to-peak amplitude of the signal prior to the adder is estimated to be in the millivolts range, a voltage reference of 1.5 is adequate to offset the signal above 0 volts. After the offsetting step, the analog portion of the circuit is complete and the signal needs to be digitized in order to record it, to display it, and to enable further digital processing steps. This is done with a circuit called an ADC, which is available in integrated circuits format. However, the goal for PolyCortex this year was to integrate a microcontroller in the circuit design of the acquisition board. Since some microcontrollers include ADC modules into their design, it was decided to use the ADC components of our chosen microcontroller to do the digital conversion. The microcontroller we chose is the STM32F4, which is a 32-bit ARM Cortex-M4 design. In order to program the microcontroller and to allow it to communicate the EEG data, an FTDI interface is used to bridge it with the computer via a USB port. The developed microcontroller circuit is not testable with our SPICE software as it is not yet quite ready for use on one of PolyCortex's board yet. Its integration is planned for the April 2021 competition. Before moving on to the next step in the signal pipeline, which is the software, let's talk about the power circuit necessary to provide the analog processing stage and the microcontroller the power levels they need to function from the USB's 5V power. For the analog power rails, the USB's 5V is fed directly into a 3.3V buck converter to provide the analog positive supply rail. The output of this converter is then fed to a charge pump inverter to provide the analog negative power supply rail. The digital supply rail is derived by feeding the USB's 5V into a 3.3V buck converter. The ground rail is tied to the USB's ground and is routed through the board in an analog and digital split ground plane configuration. This configuration reduces the digital noise induced in the EEG signal by the addition of a microcontroller on the board. The analog power supply is realized with an LM3671 buck converter and an LM2776 charge pump inverter, while the digital supply is implemented with another LM3671 3.3 buck converter. The software communicates with the microcontroller through the serial interface provided by the FTDI chip. It receives, decodes, filters, displays, and stores the received EEG signals. The filtering is mainly used to separate the 4 main EEG frequency bands, alpha, beta, gamma, and delta, but can also be set arbitrarily. Once the signal has been filtered, the software displays the 4 channels of the acquisition board and their frequency content in real time using a PyQt graphical user interface. The interface can also save the signals to enable later review or additional processing of the signals. Due to coronavirus, our resources were greatly reduced. Access to electronic and fabrication equipment was impossible for most of the duration of the project and was limited for the remainder of it. This made electrical prototyping impractical for most of the project, and we had to rely on simulation work to progress. This leaves our project at an awkward step where, with 2 or 3 additional development iterations, a fully integrated, standalone biosignals acquisition board could have been built. However, we are still proud of what we were able to achieve. We realized some of the objectives we set for ourselves at the beginning of the project could not be reached, and so the focus was shifted to research and to documentation in order to prepare for next year's competition. Hey guys, thanks for watching the video. If you enjoyed it, please like it. And if you want to follow the project even more, there's a link to our GitHub team in the description. Alright guys, thanks, have a nice one.